Hello friends, I am RM Guru working as Assistant Professor in Sharad Institute of Technology, College of Engineering. In the previous lecture, we have seen the various terms in the leveling, introduction to the leveling, then how to determine the reduced level by making use of collimation plane method and rise and fall method. So today we are going to study regarding the refraction and curvature error. So this is module number 4. I welcome you in this particular video lecture. So in this slide we are going to see what is the principle of equalizing backside and foresight. In leveling, the line of collimation should be horizontal when the star readings are taken. Again, the fundamental relation is that line of collimation should be exactly parallel to the axis of bubble. So when the bubble is at center of its run, the line of collimation is just horizontal. But sometimes the parameter adjustment of level may be disturbed and the line of collimation may not be parallel to the axis of bubble. In such a case, due to the inclination of line of collimation, errors in leveling are likely to occur. But it is found that if the backside and foresight distance are kept equal, then the error due to inclination of collimation line is automatically eliminated as shown in the next slide. So in this slide we are going to see when the line of collimation is inclined upwards. Let A and B, these are the two stations whose true difference of level is required. The level is set up at O as shown in the figure exactly midway between A and B. Let alpha is the angle of inclination of collimation line with horizontal and capital A small a is the true reading at station A and AA1 is the observed stop reading on A. Therefore, error observed on station A equal to AA1 minus AA, that is equal to AA1 and is equal to d tan alpha. Similarly, true reading equal to AA1 minus AA1 equal to AA1 into d tan alpha. Similarly, BB equal to, that is true stop reading on station B equal to BB1. BB1 is the observed stop reading on B. Therefore, error equal to BB1 minus BB equal to BB1 equal to d tan alpha. So therefore, true difference equal to BB minus BB1 equal to BB1 minus d tan alpha. From 1 and 2 we get the true difference of level between A and B as AA minus BB, that is fall from B to A, that is AA1 minus BB1. So thus it is seen that the error due to inclination of collimation line is completely eliminated and the apparent difference is equal to true difference. Then we will consider the case number 2 when the line of collimation is inclined downward. The stop reading on A and B are taken after setting the level at O as shown in the figure. Suppose the readings are A2 and B2 which are shown in the figure. Let AA equal to true stop reading and AA2 is the observed stop reading on A. So therefore, error on stop reading at A equal to AA minus AA2 equal to AA2 equal to d tan alpha. Therefore, true reading equal to AA equal to AA2 plus AA2 is equal to AA2 plus d tan alpha 2. We can replace AA2 as d tan alpha 2. Similarly, BB equal to true reading and BB2 is the observed stop reading on B. Therefore, error equal to BB minus BB2 equal to small BB2 and it is equal to d tan alpha 2. So true reading BB equal to BB2 plus small BB2 equal to BB2 plus d tan alpha 2. So this is equation number 2. So from equation 1 and 2, the true difference of level between A and B equal to AA minus BB, that is fall from B to A. Therefore, it is AA2 plus d tan alpha 2 minus BB2 minus t tan alpha equal to AA2 minus BB2. Thus it is seen that the error due to inclination of collimation line is completely eliminated. So in this slide we are going to see the curvature correction. For the long side, the curvature of earth affects the stop reading. Therefore, the line of sight is horizontal but the level line is curved and parallel to the mean spheroidal surface of earth. So in the figure, the instrument is shown and two lines are shown. One is going to represent the line of sight, which is horizontal, and another line is going to show the level line. And we are expected that one should get the stop reading at the second line, that is level line. So therefore, whatever the difference between the two lines, that is line of sight and level line, gives you the curvature correction. Therefore, the vertical distance between the line of sight and the level line at a particular place is called curvature correction. Due to curvature, objects appear lower than they really are. So therefore, curvature correction is always subtractive, because it has to be subtracted. The formula for curvature correction is derived as follows. Please refer the figure 5.19, where AB is the horizontal distance in kilometers, and let us denote by capital D, and BD equal to curvature correction, and DC is the radius of earth, and it is equal to radius of earth, that is R, and DD dash equal to diameter and considered as 12,742 kilometer. So from the figure, right angle triangle ABC, BC square equal to AC square plus AB square. So we can replace BC as R plus CC, because BD equal to CC, so and DC equal to R. So we can replace BC as R plus CC, and we can replace AC as R and AB as D. So we may get the curvature correction as equal to CC equal to D square upon 2R. So CC square is neglected because it is very small in comparison to the diameter of earth. So therefore CC equal to D square into 1000 divided by 12,742, and it is equal to 0.0785 D square. It is in meter, and it is always considered negative. And therefore, when the curvature correction is known, it is possible to calculate the true stop reading. So true stop reading equal to observed stop reading minus curvature correction. So in this slide we are going to see when the line of collimation is inclined upwards. Let A and B, these are the two stations whose true difference of level is required. The level is set up at O as shown in the figure, exactly midway between A and B. Let alpha is the angle of inclination of collimation line with horizontal, and capital A small a is the true reading at station A, and AA1 is the observed stop reading on A. Therefore, error observed on station A equal to AA1 minus AA, that is equal to AA1, and is equal to D tan alpha. Similarly, true reading equal to AA1 minus AA1 equal to AA1 into D tan alpha. Similarly, BB equal to, that is true stop reading on station B equal to BB1. BB1 is the observed stop. Then the combined correction, the combined effect of curvature and refraction is as follows. The combined correction equal to curvature correction plus refraction correction, and curvature correction is equal to minus 0.0785 D square, and refraction correction is plus 0.0112 D square. So we can get minus 0.0673 D square. So combined correction is always subtractive. Then the true stop reading is calculated as true stop reading equal to observed stop reading minus combined correction. Then in the figure 5.2 you will observe that AB is equal to D, that is visible horizon distance in kilometer, where H is the height of point above mean sea level in meter. So considering curvature and refraction correction, H equal to 0.0673 D square. So D equal to under root of H divided by 0.0673, where H equal to height of point above mean sea level in meters. So in this slide we are going to see the dip of horizon. So refer the figure 5.21, where AB equal to capital D equal to tangent to the earth at A, and BD is the horizontal line perpendicular to OB. Let BD equal to horizontal line perpendicular to OB, and theta is the dip of horizon. It is the angle between the horizontal line and the tangent line is known as dip of the horizon, and it is equal to the angle subtended by the arc CA at the center of Earth as shown in the figure 5.21. Therefore, theta equal to arc CA divided by radius of Earth in radians. So theta equal to d upon r, where d is tangent length of Earth at A and r is the radius of Earth. Taking CA approximately equal to AB, here in this equation d and r must be expressed in same unit. So theta equal to d by r, that is deep of horizon. So in this slide we are going to see the curvature correction. For the long side, the curvature of Earth affects the star reading. Therefore, the line of sight is horizontal, but the level line is curved and parallel to the mean spheroidal surface of Earth. So in the figure, the instrument is shown and two lines are shown. One is going to represent the line of sight, which is horizontal, and another line is going to show the level line. And we are expected that one should get. So in this slide we are going to see how to determine the sensitiveness of a bubble tube. Consider the figure 5.22 in which the level was set up at O at a distance d from the star at P. The star reading is taken with the bubble at the extreme right end, that is E. Say it is PA. Another star reading is taken with the bubble at the extreme left end, that is E1. Let it be PB. Let B is the distance between level and star. S is the star intercept between upper and lower sides. N is number of divisions through which the bubble is deflected. R is radius of curvature of the tube. Alpha is the angle obtained by arc E1. And small d is the length of one division of graduation expressed in same units as D and S. So here, by referring the figure 5.22, we will get the moment of center of bubble E1 equal to N into D, where N is number of divisions through which the bubble get displaced and D is the distance between the two divisions on the bubble tube. So here, while considering the figure, this particular figure 5.22, we get the triangles OEE1 and ACB. They are similar triangles. Therefore, R alpha equal to arc EE1. So therefore, alpha equal to EE1 upon R, where EE1 equal to N into D. So therefore, alpha equal to ND upon R. See again, EE1 upon R equal to S upon D. By considering both the similar triangles, we get this particular equation. Therefore, we get ND upon R equal to S upon D. From 1 and 2, we get alpha equal to ND upon R equal to S by D. So R equal to ND into capital D upon S, and alpha dash equal to angular value of one division in radians. So therefore, alpha dash equal to alpha by N equal to S by D into 1 upon N, that is radians. So therefore, alpha dash equal to S upon Dn into 206265 seconds, since 1 radian equal to 206265 seconds. So this slide refers to problem on correction and sensitiveness. The problem is a level is set up at point 150 meter from A and 100 meter from B. The observed star readings at A and B are 2.525 and 1.755 respectively. Find the true difference of level between A and B. So whenever such readings are given, then we are first of all we are supposed to calculate the combined correction for curvature and refraction. So therefore, it is given as 0.0673 into D square, where D is the distance between A and B. So 0.0673 into 150 upon 1000 multiplied by 150 into 1000 is equal to 0.0015 meter. So therefore, the correct star reading equal to observed star reading minus CC. Therefore, it is 2.5235 meter. Then combined correction for curvature and refraction to star reading at B equal to 0.0673 into 100 square divided by 1000 square. It is equal to 0.000673 meter, and it is equal to 0.007 meter. So therefore, correct star reading equal to observed star reading minus CC, that is 0.007. So therefore, it is correct star reading is 1.7543. So the true difference of level between A and B equal to 2.5235 minus 1.7543, that is 0.7692 meter. That is to say that there is a fall from B to A. So here we can solve one of the problem based on the sensitiveness. When the bubble is at center, the reading on the staff 100 meter from the level is 2.550. The bubble is then deviated by 5 divisions and the staff reading is 2.50. If the length of one division of the bubble is 2 mm, calculate the radius of curvature of bubble tube and angular value of one division of the bubble. So in order to solve this particular problem, first of all we can calculate the staff intercept. Staff intercept is calculated as difference between the two staffs, that is 2.550 minus 2.5, that is 0.50, and the bubble deviation has been given, that is n equal to 5 divisions, and the distance between the two divisions is 2 mm, that is equal to 2 divided by 1000, that is 0.002 meter. So D equal to 100 meter and B equal to 0.002 meter. So from the relation that is R equal to ND into D upon S. So N is known, that is 5, small d is 0.002 and D is 100 and S is 0.050. So it is 20 meter. So similarly, sensitiveness of bubble tube can be calculated as alpha dash equal to S upon ND into 206265 and it is 20.62 seconds. So the radius of curvature is 20 meter and the angular value of one division is 20.62 seconds. Then we will try to solve another problem. I will read the problem. A bubble tube of level has sensitiveness of 20 seconds per 2 mm divisions. Find the error in the reading on the staff held at a distance of 100 meter from the level when the bubble is deflected by 2 divisions from the center. So here we are going to know that angular value of one division is given by the expression alpha dash equal to S upon ND into 206265 seconds. Here alpha dash equal to 20 seconds and S we don't know, and N equal to 2 divisions and D equal to 100 meter, that is distance between staff and level. The previous problem is your homework. Then we will see the another problem based on the finding the height of lighthouse when the distance of visible horizon is given from the sea level. The distance of lamp from the station is 30 km and you are supposed to find out the height of lamp house. So in the figure 5.1 the level line is shown and over which the lighthouse is shown, and the point A is the point of horizon and the distance between the lamp and the point of horizon is 30 meter. So we are interested to calculate what is the height h of a lighthouse. So generally the lamp is visible above the horizon due to combined effect of curvature and refraction. Therefore we can calculate the h, that is the height of lighthouse, equal to 0.0673 d square, where d equal to 30 km and therefore h equal to 60.57 meter. Therefore the height of lighthouse is 60.57 meter. This is the problem related to finding the visible horizon distance and depth of horizon, in which 50 meter high object is given and radius is 6370 km is given. So by using the relation h equal to 0.0673 d square, first of all we are going to calculate the visible horizon distance d, and it is equal to 27.26 km. Then by making use of the formula theta equal to d upon r, where theta is depth of horizon, the depth of horizon theta equal to 27.26 divided by 6370 kilometers. So in order to convert the radians, we are supposed to multiply by 180 into 60 divided by pi. So whatever the value we are going to get, that is in minutes in place of degree, that is 14.71 minutes. Then we are going to see the reciprocal leveling. We are already found by the principle of equalizing backside and foresight distances that if the level is placed exactly midway between the 2 points and staff readings are taken to determine the difference of level, then the error due to inclined collimation line curvature and refraction are automatically eliminated. But in the case of river or valley, it is not possible to set up the level midway between 2 points on opposite banks. In such a case, the method of reciprocal leveling is adopted, which involves a reciprocal observation from both banks of river or valley. In reciprocal leveling, the level is set up on both banks of the river or valley, and 2 sets of stab readings are taken by holding the stab on both banks. In this case, it is found that errors are completely eliminated and the true difference of level is equal to mean of 2 apparent differences. So in this slide we are going to see when the line of collimation is inclined upwards. Let A and B, these are the 2 stations whose true difference of level is required. The level is set up at O as shown in the figure, exactly midway between A and B. Let alpha is the angle of inclination of collimation line with horizontal, and capital A small a is the true reading at station A, and AA1 is the observed stop reading on A. Therefore, error observed on station A equal to AA1 minus AA, that is equal to AA1, and is equal to d tan alpha. Similarly, true reading equal to AA1 minus AA. So we will consider the case 1, the correct stop reading at A equal to A1 and correct stop reading at B equal to B1 minus E. The true difference of level between A and B equal to H equal to A1 minus B1 minus E, that is fall from B to A. In second case, correct stop reading at B equal to B2, which is very near to B. So correct stop reading at B equal to A2 minus E. So the true difference of level H equal to A2 minus E minus B2. And then equating equation 1 and 2, we get 2H equal to A1 minus B1 minus E plus A2 minus E minus B2. So from that we can calculate H equal to A1 minus B1 plus A2 minus B2 divided by 2. So A1 minus B1 is going to represent the apparent difference when the instrument is set up at first position, and A2 minus B2 is the apparent difference when the instrument is set up at second position. Therefore, it is observed that the error is eliminated and the true difference is equal to the mean of 2 apparent differences of level between A and B. Then we will try to solve the problem on reciprocal leveling. In the operation involving reciprocal leveling, 2 points A and B are taken on opposite bank of a river. When the level was set up near A, the stab readings on A and B were 2.245 and 3.375 respectively. When the level was set up near B, the respective stab readings were 1.955 meter and 3.055. So find the true difference of level between A and B, and what is the RL of B? That of A is 125.550. So in the first case, the apparent difference of level is nothing but difference of 2 stab readings, that is 3.375 minus 2.245, and it is equal to 1.13. So it indicates that there is a fall from A to B. Then in case of second setting, apparent difference of level equal to 3.055 minus 1.955, that is equal to 1.10 meter. So the true difference equal to average of 2 apparent differences. Therefore 1.13 is the apparent difference for the first case, whereas 1.1 is the another apparent difference in case of second setting. So average is 1.155. So the RL of B equal to RL of A minus true difference, because there is a fall from A to B. There is fall from B to E, that is 124.5 minus 1.115 equal to 124.435. Then again we are going to solve another problem where the instrument setup is near A and the stop positions were A and B, and the distance between AB is 500 meter and RL of A is given is 525.5 meter, and we are supposed to calculate the true RL of B and the combined correction for curvature and refraction and the collimation error, and we have to see that whether the line of collimation is inclined upward or downward. So this is the figure. So first of all we are going to calculate the true difference of level between A and B, and it is calculated as difference between the two stop readings at A and B. That is 2.595 minus 1.155 plus 2.415 minus 0.985 divided by 2. So these are the two apparent differences, and it is equal to 1.435. Therefore RL of B equal to 525.5 minus 1.435, since there is a fall from A to B. Then we will calculate the combined correction for 500 meter, and it is equal to 0.0673 into 0.5 bracket square equal to 0.0168 meter. It is always negative. So let us assume that the line of collimation is inclined upward. So this is the assumption, and let's consider the collimation error in 500 meter is E. When the error is positive, correction will be negative, and vice versa. So the correct stop reading at A equal to 1.155, which is given, and correct stop reading at B equal to 2.595 minus 0.0168 minus E. So true difference between A and B equal to 2.595 minus 0.0168 minus E minus 1.155, and it is equal to 1.432 minus E. So from equation 1 and 2 we get E equal to minus 0.0118. Since the collimation area is negative, whatever the assumption we have made is wrong. So therefore the line of collimation is actually inclined downward. Thank you friends.